Example, we're going to look at a familiar looking transfer function, and that's the transfer function for a single degree of freedom spring mass dashpot system. Our goal here is to look at the root locus plot for three different cases. One where we vary the stiffness parameter of K. Second case here where we're looking at the variation in the stiffness, or I'm sorry, the damping parameter of C. And then the third case here looking at the mass parameter of M as we vary that and hold the other two fixed. Well, this isn't exactly a feedback control system that we've been focusing on here for the last couple weeks, but it is a way to sort of easily show the root locus rules. In particular, it's a problem for which we already know the answer. That is, this is a second order problem. We've actually looked at this many times in terms of what root locus plots to expect back. So consider this example as being an introductory one, where we're not really trying to learn the result, but we're just becoming more familiar with the root locus rules. And as it says here, it's important to go back and compare the results we have here with the results that they show there in section 11.1 of the textbook. Okay, if we're going to be in a position here at part A of varying K, we're going to treat K just like our gain parameter for a closed loop feedback system. So what we want to do is we want to make the leading term here a 1. So we'll divide through by ms squared plus cs like this. And what we see is that we get a characteristic equation that looks informed just like what we have for the closed loop feedback loop. This here will be n over d, where n over d, if it were a closed loop system, it would represent the numerator and denominator of the open loop transfer function. So think of it in those terms, but in fact we're really applying it to just a simple spring mass dashpot system. So let's go through our rules. Rule number 1. Here we have the number of zeros equal to a 0. The number of poles, it's second order for D, so that's 2. So we know that we need to look at the maximum of NP and NZ. And the maximum of those two, which is 2, tells us the number of branches that we need to expect. No surprise being that this is a second order transfer function. So in terms of our terminology here of open loop, our open loop zeros, we have none. Our open loop poles, we have 2. One of them is a 0 and the other is a -4. So if we go back and look at the rules that we have, where we know that we start at our poles, so our root locus plots are going to start at P1 and P2 for K equal to a 0. And they're going to end at our open loop zeros. Since we have none, that means that they both end up at infinity. Let's look at rule number 4. Rule number 4 says that we need to look first to see where our open loop zeros and poles are. We have pole here at the origin, and we have a pole here at -4. So I'll draw a line down here to indicate that that's where our other pole is going to be. Let me extend my axis about like that. Now, what rule number 4 says is that we need to look to the left of an odd number of poles or zeros on the real axis. Well, what that says is that the region here, which I'm going to show as a red line between P1 and P2, we know that is going to be part of the root locus. So the part of the real axis which is between P1 and P2 will be part of a root locus. However, that to the left of P2 will not be. So we don't expect to find any of the root locus to the left of minus 4. Okay, rule number 5. Rule number 5 tells us that our asymptotes for a root locus, as in this case k goes to infinity, is going to be intersecting the real axis at the sum of P1 plus P2, there are no zeros, divided by the number of poles. So what we have here is 0 minus 4 divided by 2. So that's going to come away at minus 2. So I'll draw in that line because that's going to represent our asymptotes as k goes to infinity. The angles, well, that's given by 2k minus 1 times 180 divided by np, which is 2. So it says that our asymptotes then will be represented by 180k minus a 90, and we start putting in integer values for k. We see one of them is at 90 degrees, another at 270. So therefore, our dashed lines there represent those asymptotes. Okay, now we need to find our breakaway and re-entry points. So breakaway, re-entry. We find this by looking at the derivative of n over d, or open loop transfer function. So that is, for this case, dds of 1 over 2s squared plus 8s. And we recall how to differentiate a quotient. Well, there's nothing on the top, so this is going to end up being a minus 4s plus 8 divided by 2s squared plus 8s squared. And those breakaway re-entry points are going to occur when that derivative is a 0. So we solve this and we see that we have this occurring at s equal to minus 2. So if we combine together 5 and 6, what we see is that our breakaway points truly occur at minus 2, and the asymptotes pass through a minus 2, so that dashed line there represents our root locus once it breaks away. So as I put this all together, this here represents when k is a 0, as well as the minus 4 case. We have, as it moves away from there and moves away from this one, they hit here. And this one here we see goes away at 90 degrees, as rule number 5 says. And this one here breaks away at 270. Like that. So this represents the asymptote here for k going to infinity. So in summary, as always, our root locus starts at our open loop poles, in this case 0 and minus 4. They end up either at the zeros when they exist, and we have none here, or at infinity. And so we find out where in the real axis this occurs. This happens between P1 and P2. That's from Rule 4. We find where our asymptote intersects the real axis. We find the angles at which it does. We find the breakaway points, and since the breakaway points lie on the asymptote, that tells us that the root locus goes along that straight line at 90 degrees. So this is a fairly straightforward application of our rules.